Okay, so template is basically your model, right? So you have expected, you already know some expected signal. Based on that, you can make many templates, and then you try to filter out. So we will deal with that later, that how it works. Okay, so to do that, first you have to run this particular cell, which actually imports. So this notebook is based on basically on Python only, right? So this actually, I hope you know some of the packages. So these are the libraries called NumPy, right? And Matplotlib, which is used for the plotting. SciPy is a scientific Python library which has many objects in that, right? So for example, we are just importing some signal as sig in this, right? And this H5PBY is basically to import your data file, which I shared in the HDF format, the data and the template, right? So just run it. It should be running. Okay. So as I mentioned that we need, first of all, we need the data file and the template file, right? So just try to run this first. This will may ask you for the permission. If you just run this. Okay, maybe first time it will ask your permission. Did it? Huh. So this will, so this will actually mount your drive here, all the content, right? So if you upload your data file there, so it should be like this in the folder name my drive, right? Should be in the my drive, this data file and the template file, right? So this data is basically 16-second long data. It is already there, right? Sampling frequency, I hope you know what is sampling frequency, because this is a discrete data. It's not a continuous data, time series data. So it has some frequency of putting samples, right? It is 4096 hertz, right? And it is also given there that your signal may be there in the first 12 seconds of the data, right? So you can be assured that the rest of the 4 seconds should be pure noise, right? Signal may be in between 0 to 12 somewhere. That's what we have to find out. Okay. And your template waveform is also a 1 second that we will see when we plot it. So just try to run this. Okay, so let me know if you are able to run these two cells. Yes, sir. Okay, the next one also, template file. Okay, so what we are doing here, we are actually just loading the file, which is in your SDF format, right? So this R means you're reading the data. Okay. Then because this SDF file has some groups inside, right? So there's a group called strain data. So we are extracting the strain data into the variable called data, right? And we just close it, right? And as I told you that it is a 16-second long data. So we are just making one array of a time series, right? So this is just a way to make any array. So we are using a range, yeah. So a range, I think it is array range, because you can give an range because you are not making array manually, right? So we know that our data starts from 0 and the 16 second. So we are going from 0 to 16 in the step of the delta t, right? So the sampling frequency. So what should be the delta t? Then that means the difference between two time. 1 by not 16. 1 by your frequency, sampling frequency. That will be delta f. If you do 1 by t, 1 by 16 will be delta f in the frequency domain, right? You can actually, if you want to see what it prints, you can actually print it, right? Time. Okay, so this is your series. So it's starting from 0 going up to 16, right? Okay. So next, similarly, we are uploading template file here, same way, right? And but we are just changing the range, because now template will have is a 1 second long. Huh? Template is a 1 second long, right? So because in case we do not know what is the time of, so we can change here actually, but we already know it is 1 second, so we are putting this here. So 1 second multiplied by sampling frequency, so it will change into the final time, right? And again, in the, we're going in the step of 1 by fs, right? This also you can try to log, see. Okay, so once we have,
I was just successful to load the collab, and it says that the collab is not authorized, so I should.
so what it says, maybe it will ask you, or
The two options are cancel and run anyway.
kya?
It says that this book is not authored by Google, so
Haan.
cancel or
Run anyway. Run anyway. It may ask your permission to go to the maybe reading, not reading, but whatever, drive content. Yeah, that's fine. Okay, so next, once we have uploaded, we have defined your data very well, we can try to plot it, right? That how it looks like. Okay. So again, these are the commands to plot the data. So PLT, because we have defined our matplotlib as PLT, because so we are using PLT as a variable. PLT.figure just sets your figure size and all, and time and data we are plotting it here, right? So you can see this is your raw data, what it looks like, right? You may notice the strain here, right? So it's 10 raised to the power minus 19, right? And that's why you may have heard that gravitational wave signal are smaller than the size of the proton, right? Because we have noise in that order. Signal may be of this order, maybe less than of it, right? Okay, I think these variables are visible because I did not make them large. Is it visible on the screen? These labels. Okay, fine. So this is your data, this is your raw data, and this is your template, right? So this is a modeled template waveform. So this should be your expected GW signal, right? If you can see directly, right? So you can see the frequency is changing here, right? It's getting higher, and amplitude is also. Yeah, so these are model waveform.
That is what
phenomenological, basically. Midway between theory and.
This is not the data.
This is your template. Data is here. This.
Yes, sir.
Right. So we will use it to search here, right? So you can see it's a 1 second template, right? Length and the amplitude of the template will change according to the masses, right? So this should have some particular intrinsic parameters, mass and spin, right? Which is not necessarily to know right now, because we already know the signal. Okay, so now thing is that how we can find the signal once we have data. So we can try these three methods. First is just to band pass the filter, because there might be some frequencies in our data which is of no use for our case, right? So we can remove those frequency, and then we may try to see the signal present there, right? So it can remove the unnecessary frequency, right? Next will be time domain cross correlation, right? So we can, the cross correlation. Correlation. There's a multiplication of two arrays, right? A or B, and we will we move one array to on top of each other and try to see the output, right? Yeah, we can normalize that also. right? And the next is the optimal match filter, right? There we actually use the template, right?
It's like any of them. We are
And then
some of the time series data analysis, like Arma and Go, because the data doesn't seem to be stationary. It's not only fluctuating about zero. Can we make it firstly stationary and then apply Arma model?
no, but how you will make it stationary? It is there, right? So GW real data is always non-stationary, right? These parameters, the property will change in the time, right? So this particular data is a simulated one, right? So this guarantees that it is stationary right now, right? The real data is not stationary.
This is also -2 to 2.
No, that does not determine the property of stationary.
But like sir, more generally the stationary data only fluctuates around zero.
So if you so if you make a histogram of this data, you can see, right? It should be around zero, right? That you can try, right? Zero being the mean value.
The mean must remain around zero.
Huh.
For stationary, right? So like for stationary data, the mean will remain around zero. Can be concluded from the very it remains around zero. But sir, like question like you are asking is quite trivial. I don't know what is trivial. Like what is stationarity? Like it will be around. So like because generally the stationary data are associated with the Gaussian point, and not only Gaussian, it will associate with the normal, standard normal. That's what that way that Gaussian belongs to its standard normal has mean at zero. So it can be like scaled to normal. Every Gaussian distribution, we can scale it to standard normal, right? By a simple shift of random variable. Suppose you have y equal to some random variable with mean a plus bx, where x is also a random. You can just do a transformation of y minus a upon b, which will be a standard normal random variable, which means zero and variance sigma. Like it is an assumption that generally stationary data some multiplicative factor into exponential one of yes. Using so like we can like translate every random variable which is Gaussian to a standard normal distribution which has mean zero, and which is generally associated with such data, like stationary data. The data is not stationary. We make it stationary. Like that's where actually the time series of course of time series started. Like if you have a non-stationary data with some periodicity or something, you apply log functions, other functions like that. Log function will be applied to remove the periodicity of the data. Like if the data has a period of 6 months, 12 months like that, you remove that period possibly. It might not get for this, it is not zero. That's why I say
it is not
it is fluctuating between plus 2 and max, so it will be around 2 only.
No.
Like
Just try to plot.
मतलब सर उसका मीन कैसे होगा ना वो देखना पड़ेगा. वो stats का इसमें आती है
If you just plot the histogram, it should be around zero. May not be perfectly, but it should be. Huh.
Yes.
Yeah, that's a definition of standard.
So like the state note that the stationary data is assumed to be generated from a Gaussian noise or not standard noise. Whenever even if you do a linear array, there the random noise is taken to be having a ZT variable, where ZT itself is a standard normal random variable. We only know one distribution. That's all. answer the reason like for
All the
doing.
considered statistical process must eventually
Okay,
follow.
now I got your question. Like, what is so special about standard? You are asking this.
What is special about stationary noise that we have need to be
Stationary noise. If you have sufficient number of data points, it will be concluded from central limit theorem because every other distribution can be like converse to a Gaussian one or standard normal one. We can say that the noise associated with data will be normal. Although like for environmental data and those things that is like very near it.
So see this plot. So
Yes,
this you can see this is around zero, around zero, right? Histogram.
That's
So that is expected. Okay. So this is just a histogram. Just use this command data and range. Okay. So we'll go one by one that how we can find the signal, right? So first is the band pass filter, right? So as I explained that in any band pass filter, you remove some frequency, right? So some unnecessary unwanted frequency, right? So to remove that, first we have to know that which is our area of concern, right? Where we want our signal to be more powerful than others. So there will be a range, there will be a band of frequency where there will be maximum power of signal, right? So first we have to know that what is that range. Once we know that range, then we can remove all the other frequency, right? So for that, to know those frequency range, so we plot what is known as the power spectral density, right? So this actually takes you into the frequency domain, and there you can see that at each bin, what is the power of the signal or noise, right? So that we can know where the power is maximum, where the power is the minimum, and then we can actually extract the band, that particular band, right? So again, there's to plot this power spectral density or ASD. ASD is the square root. Again, there's a function in Matplotlib itself, right? plt.psd, and there you can see I'm using the data, and what I'm doing here, I'm actually taking the data which has no signal, right? So as I mentioned that it is already mentioned that the data has the signal is there in the first 12 seconds, somewhere 12 seconds. So it is sure that the rest of the 4 seconds should have pure noise, right? So we want to know what is the power of that pure noise, right?
So by knowing that particular noise in the 4 second, we can find what will be the noise in that data domain. And
Yes.
remove it.
So we can know what is the power in each frequency bin. In the case of pure noise.
So and that is how we are going to remove.
Yeah, yeah. So we will know, then we will know where the power is maximum, power is minimum, right? Similarly, we will know what is the power of the template, the signal.
Yes.
Right. Okay. So that's why I'm doing. I'm just slicing this data here. So I'm going further, 12 seconds further, right? So this means I'm just taking the data after 12 seconds, right? Okay. So,
values are very large here.
huh?
Like frequency values that those are very large. Once you have to
No, it's very low actually.
it's very low.
You can see the frequency will okay. Frequency value will be, yeah, it will be. So the band is I think start from 10 to I think how much 4,000 I think hertz, right? But the other area, but what is the we already know that where we detect our signal, right? So there's a particular band of the detector itself. So usually we deal with 4096 10 to starting from 10 hertz to 4096 hertz.
So we can easily remove the noise from the noise is much of higher.
Yeah, but signal Yeah, but signal will have certain frequency also, right?
Yeah.
So so we expect that that signal should lie in the lowest power range of noise, right? So suppose if you see this figure, right? So it has 100 hertz here and 1000 hertz here. So this area you see is it has a minimum power, right? So we expect our signal to lie here. If it lies here or here, then we cannot detect it because the noise is too high there. So this is the limitation with the earth-based detectors.
Natural to expect the signal in that domain, or the signal can be.
Yeah, no, signal can be any range, but so it depends on sources. So we are detecting, let's suppose, black holes, right? So we know what should be the, or what would be the masses of the black holes, right? So it starts from 5. So there's a range, not 5, above than 3, because 1 to 3 is for neutron star, right? Solar mass. So 5 to we can go up to 500, and we can calculate, because we have the models, we can calculate what should be the final frequency or the lowest frequency of the signal. It always lies in that range. That's why we are able to detect it. If you go to very low frequency sources, let's suppose pulsars, right? It's very low frequency sources and it remains constant almost, right? So we cannot detect by these, cannot be detected by these detectors, earth-based detectors. So we need some other maybe space-based detectors, which should be in future, right? Similarly, there will be some sources which has very high frequency that will be also be out of the band, right?
Technically, we cannot observe merging of two neutrons.
Exactly. Yeah. So we'll always see. So if you see this particular signal, so this is a black hole signal, a model. So you see this part, right? This has a merger part. So you see the very high frequency and the very high amplitude region. This is where exactly the two black holes are merging. This will have the highest energy at that time. And then when we have merged it, then it's called the ring down part, right? Then they actually just rotate. That's the part. But if you see try to plot, or if you see a real waveform of the neutron star, you will never see this part. So this will not come in the band. It will have a high frequency. Hmm? Last में जो बोला उसमें
As it is a very high frequency, we will also end at much lower time.
no. It will take him a long time.
So
So
why won't the frequency would be?
Huh?
So why won't the frequency would be here to be seen?
frequency.
And the merger of neutron.
So what happens? So you have very high heavy objects, right? So heavy object will have very less cycles first because they are heavy. They will come together very fast, right?
So
So
we are
the
talking about sensors.
sensors.
We are talking about the capability of the sensor to send the high frequency. I thought
Yeah,
that-
you can say that.
So the actual waveform will only have the lower frequencies, then the actual gravitational wave itself has higher frequencies as well in the peak.
Yeah,
And
yes,
our waveform will only show the lower contributions.
yes. So for the black, in the case of black hole, we can see all the contribution in the data. But for neutron star, you may not see, because it's very light object, right? They will rotate around each other for a long time, right? They come slowly, and when they come very close, they rotate very fast, very fast. Black hole will not do that. They will rotate and they merge together. So they will not have very high frequency at that time.
From effect, you don't know how later it become kind of equal 100 after the merger of the planet.
Yeah. There are some yes. Yeah. There's a whole study of this ring down. This ring down region. This ring down region has those effects. This spinning black holes have this.
Being the singularity of the
Not singularity.
we are not talking about this.
Hmm.
There would be some sort of a reflection after some time of
Yes, but that is beyond the scope of this. Yeah, there's a whole lot of study on that region itself. Okay, so we have this ESD of the data. Similarly, we can plot the ESD of the template, right? So same thing we did with the template, right? So now you can see here the template has the power, maximum power in here, right? It may be around maybe around 80, right? This might change according to the masses of the black holes, right? Okay, in the spin. Okay, so this region is this bump you see, it is mainly because of the merger part and the merge, right? This part. Okay, so if we plot it together, so in this plot I just plotted it together, the data part, data ESD and the template ESD, so that we can know what should be the our range of extracting frequencies, right? So you see this part up to here, the noise is lowest in terms of power and the template has the highest power. So this region, it should be our region to band pass the data, right? So we can remove all other frequencies and we will focus on this part, right? This is how we know. Okay, so once we know this frequency range, we can use a band pass filter. So this is around 80 and maybe this is around 250. So we can apply a band pass filter having frequency range from 80 to 250 hertz, right? Okay, and why we're doing it? Because we know that and in that region the noise is lowest and the template has the highest power there, right? So this is just again we are importing it from SciPy. It's called Butterworth filter. You can read more about it, about this Butterworth filter, how it works. I think it actually tells you here itself if you click here, right? So after bypassing the data, you can actually, if you plot it, you can actually see some excess power in the noise, right? You can see, okay, there's some around 6 second, there's some power, excess power. This may be because of anything, right? But we have some idea. Okay, after band passing it, we are getting some power here. So this may be our area of concern. Okay, so band pass data tells you there may be a signal there, right? Now next is, as I told you, there's another way of doing it is to cross correlate it in time domain itself, right? So time domain cross correlation is simple. You just correlate your data with the template, right? So again, we are just using again NumPy function here, right? So NumPy has this function correlate, and this will tell you the correlated data, right? So we can do both. We can correlate our raw data, right, without band passing it, or we can correlate with the band pass data as well, right? Not a much difference, right? So we have plotted it both here, right? So we are plotting it with band passed one on the raw one, right? So first one is this time domain cross correlation data, and which is raw data, right? So this also tells you that there is some excess power somewhere here between 4 to 5, right? But you may see some difference in this plot and this plot is the see the timing of the peak.
yes.
Right? It is at the 6 and it is at the around 5. That is because it is offset. This x-axis is not time. Basically, it's offset between data and the template. The template itself has a 1 second length, right? So that's why you get the peak when the template is like completely overlaps with the data, right? So they will be offset of around 1 second. That's why you get the peak here. This may come from some other random reason, right? So this is a simulated data, which is mostly Gaussian. You saw in the real data, you might get many peaks, many such peaks in the real data, right? Now, what we can do more about it? So we have done this cross correlation in the time domain. We can do the similar thing in the frequency domain, right? And why we do the same in the frequency domain is because we already know that from the ASD, we know that which frequency bin has the lowest power and which frequency bin has the highest power. So the power is not same in each frequency bin, right? So what we can do, we can divide that power in the frequency domain to normalize the data. So right, suppose there may be some particular bin which has the high power, right, in that bin. So we can divide the power with itself in that bin so that it become 1, right? So if there is signal there, what will happen? Signal will have the excess power, right? So we will be dividing in the pure noise spectral density, right? So if we divide in a particular bin, and if the signal is there in some part of signal is there in the bin, then it will be access to that bin, to that power, because we are dividing noise by noise, right?
Yes.
If there is signal, there will be excess power in that particular bin, right? So that's a basic definition of match filtering. It's the same as correlating data with a template, but we are dividing it with the power spectral density, right? I forgot to mention the definition, correct definition here, right? So you got the idea of why we are doing it in the optimal mesh filter, right? Because we can take the advantage of it because we already know that which frequency bin has which power, high or low. So we can divide it by that cross correlation product so that we can get the excess power when the signal is present. Okay, so this is because it will be done in the frequency domain, right? So what we are using here, we are actually transforming data into the frequency domain. So it's called the fast frequency transform. You may have heard about, fast Fourier transform. So you may have heard about Fourier transform. Then in the continuous region, then you go to the discrete region, and then there is a concept of doing it fast Fourier transform. You can read about it, the whole book on that, right? So we are transforming our data into the frequency domain by using the FFT. Now, in this particular exercise, we also need the template waveform should also have the same size, right? If a template is over 1 second long, right? Data is 16 second long. So what we do, we just add zeros so that it becomes the array becomes the same of the same length, right? So because it actually it rotates, the template actually rotates towards the data, right? So it has to be the same length. Right? So we just add the data. So 0 pad means we are just adding zeros to the template, right, here and there. Okay, so this will be padded data, and again we Fourier transform template as well, right? So this is in the frequency domain, right? This actually we are just trying to interpolate because we actually use the noise which has certain range, right? So this function is basically just interpolating it between, because why we do interpolation, because we want some particular frequencies which we're interested in, right, which may be missing in the data, so we interpolate it, right? So just interpolation, right, to here we are actually dividing it. You can see this is about the data which is in the Fourier domain. We are cross correlating it with the template waveform, and because we have moved into the frequency domain, the one function will be the conjugate of it, right? So in the frequency domain, it cannot be A dot B, right? It should be A in B conjugate, right? Because these will be complex numbers in frequency domain, right? So we cross correlated it with the template. Here the data, and we are dividing it with the power, which is our PSD. Yeah.
Sir, this variant is real to say conjugate plane is a transpose equation.
Huh?
Conjugate plane is a transpose equation.
No, these value will have complex values. So Fourier transform data will be complex.
Right.
Yes. Okay. So what we are doing, we are going into the Fourier domain. We are calculating the cross correlation, and then we will come back to the time domain because we need to see the signal in time domain, right? So we are doing here inverse Fourier transform, IFFT, inverse Fourier transform. This is in the again Fourier domain, and then we are transforming it here. Okay. So once we know our data, our time domain data, then we can again normalize it, right? By using a normalizing factor. Why we are normalizing it? Because we want, if the noise is there, it should be 1. Only signal should have the high power, right? That's why we are normalizing it. So you can see here we are doing the same thing, but we are here just summing over all the frequency values, right? This is the only difference between this and this, right? And then so this we call is a sigma square term, right? And then we divide it by the square root of it. We're dividing it by the square root of this. So this should be our definition of the signal to noise ratio, because we remove we balance the noise in each frequency bin according to their power, and then we can see the signal, right? So the power, the ratio is known as signal to noise ratio, right? So this actually tells you that how loud your signal is, right? Okay. Here actually you can just say, okay, this is loud signal, but you cannot say how loud it is, right? Because we still have no noise, right? Okay. Here you see is a ratio. You see the number here, right? So if you plot this data with the time axis, then you will see this kind of plot. So you see the whenever noise, if it is a pure noise, it is almost 1 always.
There is a data that you are using taken from the real of.
So this particular data is not exactly real data, is a simulated data, right? So real data may have many noise transient. Let's suppose you see this some power, yeah, it might come, but the real data that you might see many such peaks.
Is it because if it is simulated, we wouldn't have any reason.
Yes.
Sir, अगर simulated है उसका मतलब तब वही हुआ ना कि secondary peak rest
हाँ, secondary
peak जो दिख रही है वो सिर्फ ऐसे ही नहीं है.
yeah है, but आप देखो बहुत compared to the signal, it is very low, right? But this may also be our area of region.
What he was
Yeah. What you are saying?
So like it could be an after effect of the boom. For example,
No, it may not be that loud.
That's like, I did some research and like when scientists were trying to plot the gravitational wave which was taken. So like they tried to put in an audio. So like if you listen to the audio very close, there is a peak and it goes down. And then there is one more peak after the collision.
Okay.
Like, I think the second small peak might be explaining this.
No.
Here the signal is simulated.
Signal
What
is
about the noise?
noise also simulated. So you see, if you see this, since noise is simulated, you see the signal here.
noise distribution is not symmetric, then there can be such peaks.
There might be. I don't know what is the reason of that peak, but yeah.
So Eli would have or that's not the Gaussian perfect.
It's not perfectly Gaussian.
It's not perfectly Gaussian.
So
We can expect it may have some asymmetry and non Gaussian.
And we have to separately check how the simulated, what is that simulated, so we can infer whether that the peak is due to noise or the simulated data.
So in real data, you might see many such peaks. Like, so this is just so this up to this
So
part.
is there any range that is considered for noise or that particular peaks to be considered as noise?
Threshold.
Threshold.
Yeah. Yes. Yes.
5.5 it is. 5.5. Anything with greater than less than a 5.5 will be considered as a threshold.
So even if the peak was till, yeah, 5.5.
At 5.5 you generally see several peaks around that big peak and one at within that 12 and 14. You can say there will be two gravitational fields. One could be loud, one could be very weak. But this is not enough. Then we do other tests, right?
Yeah. This just gives you probable signal, the trigger.
We do not
It,
stop.
yeah. It is not like it is a DW signal, because you might get many peaks, such peaks in the data.
So and we could process that data signal in that we happen to get hands on.
हाँ.
Like इधर अभी ज़्यादा time नहीं लगा, तो हमने directly click किया and we can plot the whole data, right? But there we would have more data points.
Yes. So this is
Only 60 seconds.
yeah. This was just 16 seconds. So if you if you go to this source, right?
Yeah.
DWSC.
What to do with physical data?
So you go there, data. So there is a event data as well, right?
Here the download data consists of
Yes, this will be real data. You see, right? So data have different frequency, sampling frequencies, 4 kilohertz, 16 kilohertz. So this was 4 kilohertz, which we used, 4096. So this is a timeline, right, of this particular data. P, GK. Yeah, so you can download and do the same thing, actually.
What is the current frequency of observations for that?
Current frequency band, you mean?
For the current event frequency.
No, event frequency will depend on event.
He's asking for the sample will be the at least the detector is recording.
16, yeah, this 16
You just
kilohertz.
down sample it.
Huh.
40 or 16 kilohertz.
Yes.
In 1 second you will see many.
So this is the whole data we actually we are analyzing it. But then there may be event data. So there's a catalog of
You have a signal, how fast you are sampling. How fast you are recording. Because if it's a
Kilohertz and the waves travel at light speed.
it is like this. You have a 10-second long data. Right? How quickly you are sampling it. So let's say sampling at 1 hertz. That means that in 1 second, you're only recording 1 point. 1 point. How your data will look like? If this is a science series, it will look like this. Which is not a very good representation. It looks like a triangular wave. If you want it smoother, then you need to increase the sampling frequency. Then 1 second now you want to record 10 minutes. Then it should make smoother. Yes. What we are doing here, we are in 1 second we are recording 16,000 data points. That's a sampling frequency. There's nothing to do with the wave frequency or something. It's sampling frequency. You want better version. The frequency of the feature of the wave. Even though waveforms are very, very short also. These are only fraction of seconds. You want to sample it really fast. Imagine if you even 1 second and you take only 10, you're not getting the true representation of the repetition.
There you can see these are the real event actually. You click on one. They just made the, yeah. So you can actually download it in the TXT format, right? And you can do the same exercise. And you should be able to see the signal. It may not be that loud because you saw it was SNR was 80 around. The peak value was around 80.
I have one of these.
So you, yeah.
But the number of entries are very different.
Number of
Entries are
how long, how big is that?
there are 16 lakh entries.
16 lakh. So it may be because maybe you have downloaded the 16 hertz.
16 kilohertz.
So
Like I have not downloaded. It was given to me by one.
okay. So just try this 4 kilohertz. So 4 kilohertz multiplied by 32 second. That will be your size of the array. That will be sample. Those many samples will be there. And event is around midway somewhere. So you can try to do that. But again, you have to do the same thing. You have to choose that area where signal is not present, right? So you have to estimate PSD from there. That's what we did here in the exercise, and then do all the analysis. So you should be able to see the peak somewhere. So this is just a spectrogram, right? So it should just shows the excess power. You see there's some little excess power here. Right? This indicates it's not very loud. That's why you don't see it much here. Detail. So you can see, right? These are the measured parameters of the signal. The masses. How to scroll this here? So these are the masses, and they must be spin. But you scroll, kyun nahi ho raha hai? Maybe you can in your laptop you can scroll it here. I'm not able to scroll this here. There will be many parameters, right? Masses, and there will be spins, and then should be SNR somewhere. So you see these are the very recent events. The top events are very recent events. Catalog 3 events. So these parameters which you are seeing here, the masses and the spin, these are measured by some other
Standalone object produce gravitation.
Huh?
Can a standalone object produce gravitation?
standalone object,
A single object produce
like single object, not binary one. Not binary one. Yeah, it's there. Neutron,
Yeah.
Neutron, rotating neutron, they also generate energy.
Yeah, perfectly spherical. With
Huh.
a deformed shape can be as
Because it provides a volume prediction.
yeah.
Yes. So the rotating neutron star generate gravitational wave because they are spongy. They are not
They are primary.
tidal effect. there may be some supernova explosion that also generate energy, right? So
That depends on the equation set or something like that. Equation sets are not very clear. Somebody said that the sound it will be hard. Sensitivity to spin is not clear. If it is hard, then it will not be found. If it is, people are trying to find those signatures. It is soft, then only it will be formed. If it is hard issue, then
I mean, astronomical calculus don't generally display much electric charge, but can signatures of electric charge be seen in gravitational waves?
so it was shown in the case of binary. You mean electromagnetic wave, right?
They can have.
yeah, that's right. Black holes are the classic objects. Classic means they can have three
The
terraces.
Nobel theorem is mass, spin, and charge. But I thought that if they are very large, they would have negligible charge. Cancel out. The averaging over the charges.
Overall, black hole you are saying
It's really like that. Like 34 masses. I mean, I want them to be charged, but I don't know if gravitational waves will show signatures of charge.
yeah, there are tests of
The random itself is a kind of a test for the knowledge.
if the black hole are completely classical objects and those frequencies and the should perfectly match. They are passing on a good analysis, which gives that the pattern of practice there. That was given by our own science. Visualization. Yes.
A rebound.
You can do an analytical best question in spiral and then margin. Oh, sorry,
Bring down.
In margin, you have to depend on the numerical. You can have already read about it.
Whatever online people, they it might produce, but those will be very
Any object who is accelerating faster than
exactly. True.
just as we have supersonic.
Yes. But it may not be detected by this Earth-based detector. That's why they are building now space-based detectors. So there, this noise PhD will be completely different. Right. So what type of signal we are detecting, that depends on the type of waveform we get, right? That's why we, you see the one template. So we have millions of such templates because we do not, because we know. So you see these parameters, these are varying, right? But we cannot know the parameter in advance. So we should have some parameter space. Yes, so we should have some parameter space ready, right?
So we have to compare with each and every
Each template, yes.
the template with which the
So-
data is more.
So let's suppose if we have some million templates, so we are doing this operation million times. What we did right now, right? Because yeah, so one thing which I actually did not focus on. So this is called a optimal SNR. I think that's what I written here. Optimal mesh filter. Optimal SNR. Why it is optimal mesh filter? Because the because this is simulated data, right? So we injected a waveform which had the same parameter as that of template, right? So it will give the loudest peak. But if we vary the parameter, template parameter little bit, you will see the peak lower, right? Because it exactly matches the signal waveform. Template waveform exactly matches with signal waveform, right? So that's why. So these parameters you see here, we do not know in advance, right? So we should have the network of templates actually, and there is a way to make them efficiently because we cannot make infinite waveforms, right?
Here the signal went at about 80 to its peak. In an actual data, what kind of peak can be?
Yeah, actually, I'm not able to scroll it. You can see the SNR. Are you able to scroll it from scroll left to? So there should be a column of SNR. Network SNR. Yeah, why it is network SNR? Because that what we did is maybe for a single detector. Because it's a one detector output, then there will be multiple detector output. Same thing is happening in every detector, and then they are calculating the network SNR. It should be quadrature sum. So you see the how much SNR you're getting. Maybe try and
They can do control minus.
oh maybe ah, yeah. It's not working. Anyway, it's fine. Yeah, you can see right. Network SNR is quite low. 6, 7. This very low actually. And these are the distance megaparsec expected distances.
How many light years?
The distance which make the arcane
Concept is
3.29.
3.26. 1 parsec. 1 parsec. It's actually about 6.
9.26 billion. So this is about one of the first galaxies.
Billion.
Not one of the first.
Definitely outside of
Hmm.
our region.
Yeah. About 9 billion galaxies.
Billion must be.
So like you went to documents, right, for accessing the data.
Yeah.
But it is not showing in the same way.
Where?
30 million.
Data means so 3,000 megabytes is about 9 data.
Oh, that's very yes.
Even the events of the case.
And so like, what is this chart?
Chirp mass.
Sound like chirp, word chirp. We call it chirp because it's the signal which is increasing in frequency. Frequency is constantly increasing with time. The word to chirp is a
But sir, they are marks, right?
well, that's the name of the signal they have called it chirp.
I was talking about Chirp mass.
Shared mass. Okay, this is some function of m and a component mass. This is just a kind of transformation. Simplify the calculation. Look at it in different ways. So then G equal to C equal to 1, the unit of mass.
So in this file, you can also see the posterior sample also. We have gone through this what is Bayesian analysis in this course, right? Bayesian, a little bit. Okay, okay. These posterior samples are based on those Bayesian
330 already.
analysis. Oh,
You show them some image.
330 is the show. Image, yeah, I had one.